So this next page of notes is there are 4 types of problems that we have here, and different things that you can do with planes and lines in space. So the first type of problem is if you want to find the intersection of 2 planes in space, and the intersection, so if you have 2 distinct planes in space, or 2 distinct planes in 3D, I probably should say space is better there, are either parallel or they intersect in a line. So obviously your planes could be parallel or they're going to intersect in a line, and we would want to find that equation of the line if they intersect. So for example, we want to find the parametric equations for the line of intersection between the planes the x minus 2y plus z equals 0 and 2x plus 3y minus 2z is equal to 0. Well, really our objective here is we want to write the equation of a line. So keep that thing in mind. That's first and foremost, that's what we're doing. So equation of a line, and it says it's in that parametric form. Well, in order to write the equation of a line, we need a point on the line. Point on the line. And we need our directional vector. And once we have those 2 things, it's really easy to write the equation of a line. Well, right now we don't have either of them. So what we can do to get a directional vector, the directional vector is going, to find it we can use our cross product, and the cross product will always find for us that directional vector. So first step here is to find our directional vector. So directional vector, and this is equal to, or how to find it, the line of intersection of our 2 planes. So the line of intersection of 2 planes is parallel to the cross product of their normal vectors. To the cross product of their normal vectors. Therefore, if we take our normal vectors here from our 2 planes, and if we take the cross product of them, we're creating this new vector. Well, that new vector that we find, the line of intersection, is going to be parallel. So that's very nice because it says as long as it's some scalar multiple. So to create our directional vector, we have our I, j, k. We have to obviously use the cross product, and that's what it says in here to find our cross product. So we have, looking at our first plane, it would be 1, negative 2, 1. So 1, negative 2, 1. And our second plane, it'd be 2, 3, negative 2. 2, 3, negative 2. And maybe jumping ahead of myself, we should probably always check first of all to see if they're parallel. And so if we look at these, if they're parallel, we know that they're going to be a scalar multiple of each other. Well, I'd have to multiply by 2 to get from the first one to the second one. If I multiply by 2, I'm not going to get that second one to work out, so we know that they're not parallel. Okay, so now going back, if we're going to have our cross product apply, we'd have 4 minus 3, so that's going to give us a 1. We'd have negative 2 minus 2, which is negative 4, but remember this is opposite, so that would be a positive 4. And our last one is going to be 3 minus a negative 2, which will give us 7. So there's our directional vector, which we need that because if we go back to the equation of a line, we need our directional vector. Well, the next thing that we have to do is we have to find a point that is on the line. Basically what that means is that we have to find a point of intersection. And then if we can find a point of intersection, we know that that's going to be on the line where these 2 planes intersect. So point of intersection, what we do for this is we're going to set the 2 planes equal to each other. Set 2 planes equal to each other. And in this situation, If we look back at our planes, we know they're both equal to 0. Therefore, we could say, hey, the x minus 2y plus z is equal to 2x plus 3y minus 2z. But that's not always the case, so another way to set them equal to each other is to just create that system of linear equations. So we have x minus 2y plus z equals 0, and then we would have 2x plus 3y minus 2z is equal to 0. And sometimes it works out really nice where you have a common multiple that will get rid of two terms. In this situation, it looks good to start. I'm going to multiply by 2. This first plane, I'm going to multiply it by 2. Then I'll end up having 2x minus 4y plus 2z will equal 0. Keep the second plane, so 2x plus 3y minus 2z is equal to 0. And now I'm going to subtract because I know that will get rid of the first term. So if I subtract everything, 2x minus 2x, great, the x's are gone. Negative 4y minus 3y will give me negative 7y. And although these coefficients are the same, it unfortunately doesn't work out very well. 2z minus a negative 2z will give us 4z, and we know that's equal to 0. Well, from here, what you can do is just find a point that works. And this one actually ends up being pretty easy. So find a point that works. And generally what that means is that you're going to want one value that should equal 0. That's going to be the easiest way. So let one variable equal 0. Well, if we do that for this particular problem, if we let y equal 0 here, well, and we want this to work out, we know that z is going to equal 0 then too. So here, we're going to let y equal 0. Negative 7 times 0 is 0. So that term is basically gone. Well, I have to let 4z then equal 0. Well, then, of course, z equals 0. So then, z is equal to 0. Now go back, and we can plug it into one of our equations. And so I'm going to go back up here and say, well, if y is 0 and z is 0, well, now what does x have to be? Well, if x is 0, the whole thing is equal to 0. That point, so now I have 0, 0, 0, which is pretty unique. Does it work on both of your planes? If I plug in 0, 0, 0, does it equal 0? Obviously. Plug in 0, 0, 0, that one equals 0 as well. So check to see if the point works on both planes. So check point on both planes. Remember, writing equations now is not unique because there's obviously more than this point that works. We're writing the equation of a line, so there's really an infinite amount of points, and somebody else may find a different point that works. So we're not just going to say, hey, this is the only one. There's actually multiple solutions to this. But now I do have my directional vector, which was given to me up here. I have a point here, and now I can write my equation of my line in parametric form. So our equation, we have what is x equal to, what is y equal to, what is z equal to. And remember, x, we take our point first, so it's 0 plus 1t. So it would just be 1t, or I'm just going to leave it as t. Well, our point is always 0, so it would be 0 plus 4t. And for our z is going to equal 0 plus 7t. So here is our parametric equation for our line, and this is that line of intersection between two planes. And for this particular one, we could come up with the symmetric equation as well because we do have t, but most of the time we're just going to write it as a parametric equation. Okay, another thing that we'll do is we are going to sketch planes in space. And these end up being fairly easy sketches. They have something called a trace. And what this is if a plane in space intersects one of the coordinate planes, the line of intersection is called the trace. So say that slowly here. If a plane in space intersects one of the coordinate planes, the line of intersection, is called the trace. So you may hear that vocab. If you have a plane that's going to be parallel to an axis, it could be parallel to your x-axis, your y-axis, or your z-axis. We can tell right away if a plane is parallel because it's going to be missing a variable. So for this one, if an equation of a plane is missing a variable, so if an equation of a plane is missing a variable, the plane is parallel to the axis represented by the missing variable. So the plane is parallel to the axis represented by the missing variable. All right, well, we have two examples here if we're going to sketch a plane. And we want to label any intercepts, so any intercepts on the x, y, or z axis, and we want to sketch the graph of the plane. Well, really, by labeling any of our intercepts, that's going to help us graph. So if we look at this, usually to label our intercepts, we want to figure out, okay, what would be my x-intercept? Well, I have 2, I have to make this thing equal 4, so obviously x would be 2. So 2 times 2 is going to give me 4, therefore I want my y and z both to be 0. For my y-intercept, okay, I don't want to have x and y, so my x will be 0. My y is going to have to be a -4, and my z would be 0. And for our z-intercept, we know that we'd want obviously 0, 0, and then a +4. So when we graph this, to start, I'm just going to graph the positive. So I have x, y, and z. And I'm going to just graph my points of intersection. So I have the point 2, 0, 2, 0, 0. So that's going to give me that first point. Then I need 0, -4, 0. So I'm actually going to really lightly, with this I can't graph lightly. We'd have to go back, and now we obviously want to go back -4. So there's 0, -4, 0. And then our last one is 0, 0, 4. So 1, 2, 3, 4. And now you can connect your points of intersection. And this gives us an idea of what this plane would look like. And this plane is bigger than this. It's not just this triangle. It extends in all directions. But we kind of get the idea of what this is actually going to look like. So, here's your plane. It's slanted. And it's obviously wider than this too. But that first sketch gives us an idea. And I just really, when you graph these, you don't have to put that part in. I just want to have maybe a portion of what the actual plane would be. So this is nice. It gives us an idea of what it is. It gives us a slant where it's located, but you're not going to have the entire plane graphed. Number 70, if, again, we want to look at our intercepts, that helps us. And in this situation, we're missing our z variable. Therefore, if we go back up to B, it tells us that if our equation of our plane is missing the variable, then we know that our plane is going to be parallel to that axis. So if I'm missing z, this has to be parallel to the z-axis. Parallel to z-axis. I still want to find my x and y intercepts. And this is still in space, so I'm still going to take account for that third variable there. So for my x-intercept, I know it's going to be 4 because it's going to equal 4. It'll be 4, 0, 0. And for our y-intercept, it's going to be 0. That would be a 2 and 0. So again, I'm going to graph, and I just graphed my xyz, the positive. Now I have the point 4, 0, 0, and I have the point 0, 2, 0. Well, now it's a lot harder to connect points because here it's 3 points. Great, I connect them. And this one I don't have that. But remember, we have to be parallel to the z-axis. So parallel to the z-axis, our z-axis is up and down. So what we can do is draw in parallel lines to the z-axis. And you want these parallel lines to be about the same length. I think it makes it look a little bit better. So I have to say, all right, whatever, maybe this is an inch here, and try to go an inch below. Do the same thing here. So go an inch above and an inch below, and I know that's not real accurate what I have. But that does make it the easiest. And then you can connect your points. So here would be our plane. And again, same situation. This is just a small segment of the plane, or a small portion of it. When really it extends, it's much bigger. But we get the idea here that of what it would look like. And so we have our z-axis. This one maybe got a little slanted, so it's not quite so up and down, which would be better. And gives us an idea. So whatever variable is missing, that's nice, because z's up and down. So we know that those lines would be going parallel to that. Those would be straight up and down. So that's pretty easy, sketching planes in space. Moving on, we have 2 tough ones here at the end. Really, they're not that bad. What's annoying about them, though, is that they require formulas. So we do have to remember formulas. The first one, we want to find the distance between a point and a plane. And remember, these things are in space. And obviously, I guess we can't have a plane in two-dimensional sense. So the distance d between a point Q and a plane is the length of the shortest line segment connecting the point Q to the plane. P can be any point in that plane. It doesn't matter what it is. We can pick any point in the plane. Then we can find the distance by projecting the vector of PQ onto our normal vector n. Well, the nice thing about this is that we don't have to use that formula for projecting something onto, one vector onto another. There's a simpler formula for this. But the distance between a plane and a point Q, and that point Q, remember, cannot be in the plane, is given by this formula. Distance is equal to the absolute value of A times x sub 0 plus B times y sub 0 plus C times z sub 0 plus D. So it's the absolute value of that divided by the square root of a squared plus b squared plus c squared. Well, what these things are, we know that our plane is represented by the equation of ax plus by plus cz plus d is equal to 0. So that's where the a, b, c, and d come in, and obviously the a, b, and c. Well, then we also need a point, and this point Q, which is not on the plane. Our point, and I don't know why they use sub 0, but x sub 0, y sub 0 is z sub 0. So as soon as you find, here's my point, not in the plane, here's my plane, then it's pretty basic, I guess. So example, we want to find the distance between this point and this plane. Well, that's as simple as it comes. Follow our formula. Our distance is our absolute value. Our plane, if you want to, like here, your A is 1, B is -1, C is 2, D is -4. And we can say, well, it's 3 times 1, so that's 3, plus 2 times -1, that's -2, plus 1 times 2, that's 2. Then it does have to be plus D. Well, that, if we put this over here, that would be -4 would equal 0. So that would be -4. And we need the absolute value of that divided by the square root of our plane. So it'd be 1 squared. So 1b squared would give us another 1. C squared would give us 4. So 3 minus or plus a negative 2 would give us 1. 1 plus 2 is 3. 3 minus 4 is negative 1. Absolute value will give us 1 divided by the square root of 6. Therefore, our distance is square root of 6 divided by 6. Another type of problem dealing with the two is this one. Verify that our two planes are parallel, and then we want to find the distance between the planes. So obviously we can look and tell if they're parallel, and this one is super easy. As long as they're a scalar multiple, they're going to be parallel. Well, this one we don't even need that because we have 4x and 4x, negative 4y, negative 4y, positive 9z, positive 9z. Yes, so check. Yes, they're definitely parallel to each other. So we want to find the distance between them. Well, we need a point from one of these because this equation finds the distance between a point and a plane. So I just need a point. And I can take a point on this plane or on this plane. And I want to take the easiest thing possible. So looking at it, I can easily find a point on my second plane. And I'm just looking for what goes well together. And if I have to get to 18, that's a lot easier than getting to 7. And I know a point then on this plane, if I look at values, if I multiply that z times 2, grade them to 18. So I want my x and y to be 0. So 0, 0, 2. That is a point on the second plane. And you have to keep in mind that that's the second plane. But now I have a point, and now my plane, I have to use my first plane because it's a point on the second plane to our first plane, which is 4x minus 4y plus 9z. That would be minus 7, and that would equal 0. Therefore, our equation, the distance, it's the absolute value, multiply, well, I have 4 times 0 is 0, plus negative 4 times 0 is 0, plus 9 times 2 will give me 18, and then I needed that plus d, so minus 7, divided by the square root of a squared, so there's 16, plus b squared, that's 16, plus, c squared, that's 81, and 18 minus 7 is 11. I don't need absolute value, but that works. 18 plus 16 is 97, plus 16 more would give me 113. So square root of 113. Therefore, this distance is 11 square root of 113 divided by 113. So distance between two planes. Take a point on either plane, but you have to know what plane you're dealing with. So I'm dealing with the second plane. Then so I have this point. The plane has to be the other one, so that would obviously be our first plane. And then the formula is pretty easy from there. And one last type of question. We have find the distance between a point and a line in space. So we have to be very careful in these last two, the distance problems. Are you finding the previous one we just did is a point and a plane? Well, now this one is specifically a point and a line. So just be really careful with the directions because it's going to be a different formula, and obviously if you use the wrong one, we're going to get the wrong answer. So the distance between a point Q and a line in space is given by this formula, where a distance is the magnitude of vector PQ cross vector U, all divided by the magnitude of vector U. Alright, well to define what everything is, we know that we're finding the distance right now between a point and a line. Well, we have a point Q, and this is that, obviously it's not on the line, but we have that point Q. What we have to do, we have to figure out vector PQ. Well, P is any point on the line, and Q then is that point that we're going to. So you have to, one thing is figure out what is that vector PQ. Vector U is your directional vector from the line. which if I have a point and a line, okay, there's my directional vector, and you want the cross product between them. So we want to find the distance between this point, 1, -2, 4, that's like our Q, and this line. Well, the first thing that we have to do in order to apply this formula is we have to figure out what is vector PQ. So we need to find a point on our line. So that's the first thing. Find a point on the line. And really that's quite simple because you can just let t equal 0 and that will find a point for you. So a point on our line, and that's what we're finding then is point P. If we let t equal 0, our x value will be -2. Our y value, we don't have a t value, so that would just be 3 still because there's no t to plug in. And for z, if t is equal to 0, that's going to equal 1. So we have our point P, and then point Q has to be given. So then we have Q, which is 1, -2, 4. Well, we have to figure out vector PQ, which obviously very simple to do. Vector PQ, 1 minus a -2 will give us 3. -2 minus 3 will give us -5. 4 minus 1 will give us 3. And now we have to follow our directions. We have to take the cross product. So I, J, K, vector PQ cross vector U. So 3, -5, 3. Vector U, remember, is your directional vector from the line. So our directional vector, if we go back to this, it's always going to, that direction is always multiplied by the t. So it's 4, 0, -1. And find our cross product. So we do that, that would give us 5 minus 0, so we have 5. This is negative. That's a -3 minus 12, so that's a -15. We'd make it a positive 15 then. And we'd have 0 minus a -20, so that gives us 20. So we've applied our cross product up here. Now we need the magnitude of it. So that's pretty easy to calculate, the magnitude. And then remember, it has to be divided by the magnitude of u. And the magnitude of u is this, is our directional vector for our line. So if I look at our line, that's going to give me the 16 plus 0 plus 1. So that's square root of 17. The magnitude of this, 25 plus 225 plus 400, will give me the square root of 650 divided by the square root of 17, and this is approximately 6.18 units when you calculate it. And I know that went really fast, but that's because that bell rang and I have to start a class. But if you look through this and read it again, u is our directional vector, so keep that in mind. Remember, your cross product is not commutative, so you have to go in order. P is a point that is on your line to start. Let your parameter equal 0, or that t equals 0. Q is your point that you're trying to find the distance between, so it's very easy to create that vector. Cross product with vector u divided by the magnitude of u. And the homework assignment for this is lengthy. There's just so many things in here. A lot of different applications with different formulas. So make flashcards for yourself. Remember the formulas. If you have the last things that we did, the distance between a point and a plane compared to the distance between a point and a line in space. And there's just a lot of little things. The other thing that I think is tough is finding that number 5, if you go back in your notes, the intersection of two planes in space. To me, that one is too, it's kind of a process that, practice it a couple times. Once you understand the process, that first I have to find my directional vector. Then I also have to find a point of intersection. Well, once you have those two things, your directional vector and a point of intersection or a point, you can easily create the equation of a line. But kind of a lot of tough stuff in this section, and really review it, work hard on it. Section 6 is much easier. It's Section 6 is actually incredibly short, and Section 7 isn't. That's not too bad either. But there's just a lot of little formulas in here, a lot of little things. But the equation of writing the equation of lines and the equations of planes. Good luck to you.